Morning, folks. I think we're at our new start time, so we should kick off. I've been watching Twitter, and I've seen almost as many tweets for deadmau5 as I have for Kinesis. And I'm not sure what conclusion to draw from that. So my name is Eric Brandwein. I'm with the AWS security team, but when I joined the company about 6 years ago, I was with the team that defined and built VPC, Virtual Private Cloud, and that's what we're going to be talking about today. We'll take a look at the problem we were trying to solve, the customer experience that we wanted to provide, a couple of ways that we could have implemented it, and then we'll dig into how we actually wound up building it and what that means for us. Story's pretty simple. We are AWS, Amazon Web Services. We have the cloud. We have all of these services, things like EC2 and Elastic Load Balancing and Elastic Block Store and our relational database service that just got Postgres support, Redshift Data Warehouse Service, Elasticache. This stuff's great. This stuff is not. Customers have data centers. And so, like all good engineers, we go to the whiteboard. You've got the data center, you've got the cloud, let's just connect them together. This is going to be a very important deployment scenario for us. Andy Jassy touched on this during his keynote. We have customers, they have applications, they have resources, they have data already sitting in databases and data warehouses and cold storage on their premise, and doing a massive big bang forklift migration is unrealistic. We do have some customers that don't have any legacy. They can build for the cloud, and that's awesome. Like, we want those customers to have a great day too. But for all of the customers that already have some sort of IT infrastructure, we have to enable an incremental migration. We have to enable them to pick and choose and move at the right speed for them. We have a poster child customer here. I'm going to move to the less wired solution. Last year at this conference, Laura Gritt gave a talk entitled Drinking Our Own Champagne on how Amazon moved to the cloud. And it dealt with all of these issues. There's nothing magical about Amazon. We built our applications in our data centers, and because of that, they have a whole bunch of assumptions about the environment in which they were built. And so just flipping a magic switch and appearing in the cloud one day wasn't going to happen. And so moving Amazon into the cloud relied on VPC heavily. And we have many other customers that are in exactly the same situation that are making that exact same migration. And if anyone's interested, the talk is on YouTube. So the reason that it was difficult for us to connect EC2 up to customer data centers is that when you launch an EC2 instance, you get what is effectively a 32-bit random number as an IP address. We pick it, you have no control over it, and there's no guarantee that your instances are going to be anywhere close to each other in terms of IP address. And in fact, instances that are close together in IP address may be owned by different customers. And so as instances launch and terminate, they get smeared across this internal IP space. And there's no grouping mechanism there. So when you try and connect to a customer's data center, let's say this customer has chosen to number their data center out of 192.168.00/16. And this is a decision that they made for reasons that made sense to them. They made this decision years ago when the building was built, perhaps before AWS was even invented. And there's absolutely nothing wrong with that decision. They've got a router. Most networks have routers on them. The router has a routing table. And that routing table has an entry for that data center's IP block that says, that stays here. So as we launch instances, we need to inform that router in the customer's data center how to get to the instances. So as we launch instances, we have to add entries to that customer's routing table. And we have to add /32 host routes because the neighboring IP address may be owned by a different customer. And so as we launch instances, we continue to add entries to the routing table. This isn't the way that networks normally work. As we delete instances, as we terminate instances, we have to remove the routing entries because that IP address could be handed to another customer when they launch an instance. And so now, rather than a network that has routing table updates at the rate at which administrators make changes and at the rate at which links change state, we have a network that has state changes, has routing table updates at the rate at which instances are launched and terminated. This is very high velocity. We've got a slightly bigger problem, though. What if, years ago, this customer happens to have chosen 10.44/16? Perfectly reasonable decision. The cloud didn't exist at the time. But now we have a conflict, and there's absolutely nothing that we can put in that routing table that makes sense. There could be a 10.44.12.4 in the cloud and a 10.44.12.4 in the customer's data center, and that's just a miserable place to be. You can do things like double NAT, but anyone that's actually lived in a network with double NAT will tell you you don't want to live in a network with double NAT. So we need to figure out how to solve this high-velocity routing table update problem. And there's no single IP block that we can choose that's guaranteed not to overlap with any of our customers. And so if we're going to build VPC, customers have to be able to bring their own IP blocks. They have to be able to pick the IP range that makes sense for them. There's nothing that we're going to be able to do to solve this problem universally. We have to enable each customer to solve it for themselves. We need to aggregate routes. We need to make it so that the rate of change in the state tables on the traditional routers outside of the cloud is something reasonable. It's something that approximates the rate of change that they would have had if they were connecting just to another data center. And we need to conform with existing network designs. And what I mean there is we had an early customer, and this customer, who I may or may not currently be employed by, had host management tools that assumed that all networks were /24s. Some software developer years ago was told we need a database of all our hosts. He looked at the way we built data centers. All the networks were /24s. He went and he built. So we got a request from this customer that they needed /24 networks, and could we please support this, and how long would it be until we could support /24 networks? And the answer was it's one API call, go do it yourselves. And so if Amazon has these problems, surely our other customers are going to have these problems. They're going to have assumptions about how they've been building networks for years outside of the cloud. And it's easier to enable them to continue their network design practices in the cloud than it is to make them all conform to the way we think networks should be built. So that leads us to the customer presentation for virtual private cloud. Customer declares a VPC. They get to select the IP block that they're going to use for their VPC. They get to pick anything that doesn't conflict with what they're using already. They bring up a VPN gateway. This is an API call to us. They tell us about the VPN device on their side. We call it a customer gateway. And then we bring up a VPN connection between the two. And when BGP comes up, they get one route for the entire VPC added to their route table. So as far as the router in the customer's data center is concerned, they're just connected to another router at the end of some remote link. Now the customer can declare subnets, assign CIDR blocks to them, and as they launch and terminate instances, the routing table in the on-prem data center doesn't update at all. So with this product definition, we've solved the high-velocity routing table updates, and we've solved the overlapping IP address problem. And you're all sitting out there saying, I've seen this slide before. Like, this is just virtual networking. This isn't anything revolutionary. You can take an Ethernet switch, you can apply VLANs to it, VLANs and subnets. You just used a different name for the same thing. A lot of routers for a long time have supported VRFs, virtual routing and forwarding instances. So you take the monolithic routing table in the router and you just chop it up into multiple instances. So you just take this physical network that you already have and you ask it to make virtual copies of itself. The problem is that what we're talking about here is far outside of the design envelope for these devices. It looks the same when you're considering one customer, but when you look at it at cloud scale, it's a fundamentally different problem. And so the complexity of the configuration on these devices and the testing envelope that the vendors have don't line up with what we're trying to do. So for example, the VLAN header, the 802.1q VLAN header, uses a 12-bit identifier for VLANs. To the 12th is 4096. Most of the routers, some of them claim up to about 4,000 VRFs, but in reality, when you dig in, they've only been tested to 1,000 to 2,000. 1,000 sounds pretty good, unless you've got hundreds of thousands of customers and you're looking to the future. And they've tested to 1,000 or 2,000, but they probably haven't tested with the level of load that we're talking about, the rate of configuration change. And these vendors have a name for customers that are the first to use a particular piece of functionality in production. They call them beta testers. And that's not where we want to be. Plus, I've got a fixed ratio of VLANs to VRFs. These are both constrained resources. And now I'm going to run out of one or the other of them first, stranding capacity. But as we dig in, this gets even tougher. We're talking about big routers here. You've seen pictures of them. They're these monstrous boxes. They take half a rack or a rack, tens of kilowatts of power. They're rated in hundreds of ports and terabits of throughput. And they really are massive, monstrous boxes. But when we're talking about that, we're talking about the data plane of the router. We're talking about the fast path through the device. This is where the ASICs are. This is where all of the clever shared memory buses are. This is where the expensive hardware is. But inside the router, there's also a control plane. And in many cases, these control planes are less powerful than the laptop I'm using to give this presentation. They cost a lot more, but they're less powerful. And there's constrained bandwidth between the control plane and the data plane. And the control plane is where the operating system of the router runs. This is where your command prompt is. This is where all of the routing protocols run. And so the things that we're talking about doing here, we're talking about supporting thousands of instances of routing protocols and updating all of this configuration data. We're putting stress on the lightweight control plane. We're not putting stress on that heavyweight data plane. And of course, we want our customers to have a good day in the cloud, so we're going to buy these things in pairs, and we're going to bring up some sort of availability protocol between them. And that availability protocol runs between the control planes. So we're placing yet more stress on that constrained resource. So an example of how this capacity allocation problem can play out, these routers are configured with text files. If we say the average router configuration line is about 50 characters, it takes us about 10 lines to describe a VPC. On average, customers are using 4 subnets in every VPC. In order to describe a subnet, we need 5 lines of configuration. So we've got 2,000 customers on this device. You multiply everything through. We're loading up a 3 megabyte config file into this device. Most routers don't swallow 3 megabyte config files well. I'm sure someone out there has done the math and figured out that I just allocated 8,000 VLANs, and I just said you can only do 4,000. We actually prototyped this in the lab. These are round numbers to make the slides look pretty. We were regularly loading config files much larger than this into devices. And in several cases, it took the devices 5 minutes to parse the configuration. So you hit return, and it's 5 minutes before you get the prompt back. It doesn't mean the configuration has actually been programmed into the data plane. It just means that the configuration has been parsed and accepted by the device. That's an indication that you're exiting from the common use cases, and you're off in a very scary land. Dragons. Routers are just computers. They have strange, expensive hardware. You buy the software and the hardware from the same vendor, but it's just software. They're human beings writing the code, and they suffer from all of the problems that computers have. And they have assumptions in the testing that they do. They know how their customers are using the devices, and they test those cases. They don't necessarily know how their customers are going to use the devices. So one problem we ran into is we had a router vendor that was storing internal data structures in a linked list. And if you have 6 instances of some object, traversing a linked list of length 6, who cares? If you have 4,000 instances of some object, and every time you have to do something, you have to do an exhaustive search of a linked list of length 4,000, all of a sudden the control plane, tiny little stressed control plane, isn't happy. Another problem that we had is we had a router vendor, and as far as we can tell, this is a bug that dates back to very early versions of their control plane code. It would leak memory every time you committed the configuration. In most routers, they get stood up, a network engineer logs into them, they play with them for a couple hours or a couple of days, and then configuration events on the router are very infrequent. And with our routers, configuration updates are tied to customer API calls. Customers create and delete VPCs, subnets, change things around. We have to push configuration to the routers to reflect that. And so we have a dramatically higher, orders of magnitude higher configuration velocity. And so every time you commit the config, the router leaks a couple words of memory. We could reliably crash these things in a couple of hours just by pounding config updates to them. This is a problem that didn't affect any of their other customers because no one else was using the devices in this way. I'm convinced. Maybe the router has a faster control plane than this laptop. Horizontal scaling is a time-honored design pattern in large-scale systems. It's one that we use all the time. These numbers are artificially low. I tried to use larger numbers and the slides got too noisy, but it's meant to be a representative example. So we've got 2 silos here. We've got 2 stacks. Each of them can support 4 customers on the routers, and the routers have enough network ports and capacity to drive 40 instances worth of EC2. So I have a customer show up. I put them on the left stack. Makes sense. Another customer B shows up. I put them in the right stack. There's all sorts of interesting placement algorithms you can apply here, first fit, best fit. It's an interesting optimization problem, but we're not going to go there. Another customer C shows up. I put them on the left stack. I'm starting to consume my router and my instance capacity. Nice big customer D shows up. A launches a few more instances. And then we have customer E. And customer E looks like a tiny little customer. But it turns out that customer E is actually insanely important to us. The reason is that this is the getting started guide. This is a customer running one T1 micro. And every single one of our customers was once a first-time customer. We need that simple on-ramp. We have a lot of customers that are just getting started. And so we need to make sure that we support this use case really well. And this one instance, one T1 micro customer, just took up an entire slot on one of my routers. So we keep going. Customer F launches, and this was an enterprise. They'd been planning a large migration, so they consumed a bunch of capacity. And then customer G. I've exhausted my router capacity on that left stack. I can sell my remaining 25 instances worth of capacity to those 4 customers, but I can't sell it to anyone else. If they scale up, I can make use of it, but if they don't scale up, that capacity is stranded. That's going to drive lower utilization, which is going to drive higher prices. And even if you hit something like 90% utilization, that's an 11% price increase. That's not what we want to do. But even worse, it turns out that customer B is some social media application, and they just went viral, and they have the massive scaling event. I'm out of instance capacity on the right stack. I can hide the fact that I'm out of router capacity on the left stack for my customers. I can't hide the fact that I'm out of instance capacity on the right stack. I have to expose this to the customer. They have to go create another subnet, another VPC. This is a terrible customer experience. And as you've been seeing throughout this conference, we have customers who have scaling events in the thousands or tens of thousands of instances. That's a massive slush fund to have available in each of these stacks. So this is a very difficult way to build the network. We're basically playing Tetris with pieces that can change size and shape at any time. So we talked about a couple of product requirements. Let's talk about how we're going to build this. This is literally one of the requirements that we put on the table when we went down this path. If we're going to build this, we have to be able to host millions of customers the size of Amazon. And we must not place any new constraints on the placement problem. We have different instance types. Some of them have faster networks, slower networks, GPUs, different ratios of CPU and memory. The placement problem is already a challenging problem. The network must not add any new constraints to it. So let's talk about the building blocks that we actually used for VPC. Amazon has data centers full of physical servers. Someone has to own the sheet metal. On those servers, we host customer instances. Those instances are grouped together into VPCs. Those servers host instances belonging to multiple VPCs. Our APIs, we use hexadecimal identifiers, but in these slides I'm going to use color because it's easier. And one piece that our customers can't see from the outside is the mapping service. The mapping service is the linchpin around which the entire network revolves. It's really a very cool distributed system. So let's go back to the dark days. Physical Ethernet switch. This is how it's been done for decades in my house, in data centers around the world. If 10002 wants to talk to 10003, it's going to send an ARP request. The destination, layer 2 destination, is going to be an L2 broadcast. I'm using this MAC of IP address notation to make the slides friendlier. Mentally, you can substitute any 40-bit, 8-bit number of your choice. So the switch, we'll assume it's freshly booted. It doesn't know anything. It's going to flood that ARP request out all ports. One of those ports necessarily is going to be the host to which the port to which 10.0.0.3 is connected. 10.0.0.3 is going to say, yep, that's me. The switch is going to snoop that ARP response, so the switch is going to learn the MAC to port mapping. And so now 10.0.0.2 can send his packet with whatever layer 3 and layer 4 payload he wants. So the way that works in VPC is our guest sends exactly the same ARP packet. To run in VPC requires exactly 0 changes to the guest's IP stack, Ethernet. It is bone standard from the guest's perspective. We trap that packet, and the server sends a query to the mapping service. It says, hey, I'm 192.168.0.3. I've got a query on behalf of an Orange guest for 10.0.0.3. The mapping service says, OK. Hands us back both the physical mapping, 10.0.0.3 is located in 192.168.1.4 in the lower right corner there, and the MAC address. And so we can respond with an ARP response back to the guest. So as far as 10.0.0.2 is concerned, they just ARPed for their peer and got a response. So their ARP cache is hot, they're ready to go. One interesting thing worth noting, 10.0.0.3 never saw an ARP request. It turns out that doesn't actually matter. So again, Ethernet IP straight off the OS DVD. The guest forms their packet. The layer 2 and layer 3 source and destination both line up because this is an L2 flow within an L2 broadcast domain. We trap that packet. We wrap it with a VPC header. We then wrap it with a physical network IP header. And we send the packet directly across the physical network to the destination host. On receipt, 192.168.1.4, it just got this packet out of the blue. It was like, what the heck? So it asks the mapping service, I just got this packet from 1.4 claiming to be on behalf of Orange 10.0.0.2. Is that kosher? The mapping service responds, yeah, actually, Orange 10.0.0.2 is indeed on that upper left server, 0.3. So now that we've got validation that this is a kosher packet, we deliver it on up to the guest. So in order for these two instances to communicate with each other, the only requirement is that they have IP connectivity between each other and that they be able to talk to the mapping service. So we're getting to that goal of any host in the region can host any instance in any subnet. So I've shown that 2 instances within a subnet can communicate, and we're very good at building large IP networks. We've got the internet. We know how to build IP networks that span the globe. So this is a solved problem, and it's a problem that our network vendors solve very well.
Once that handshake happens, just talk again on every subsequent packet, or once it's been validated once, does the server accept?
So you're asking whether the mapping service query happens in line with every packet. That is a complicated question with a complicated answer, and I will go into that in future slides. The short answer is we do cache mappings. We're not pounding on the mapping service with every single packet transmit and receive. Yeah, there are large distributed systems, and then there are crazily large distributed systems, and you want to avoid crazily large. So the result here is that the layer 2 virtual topology is completely decoupled from the physical topology. I can place these guests anywhere in my data center. I don't need large layer 2 physical domains that span racks, that span data centers. So that reverse mapping on receipt is interesting. Let's dig into that a little bit. The simplest form of isolation that VPC offers is that we always interpret packets sent by our guests in the context of their VPC. So this is the exact same ARP request that the Orange guest would have sent, modulo the source IP address. But the query that we send out to the mapping service is for the gray VPC. The guest physically can't cram anything into that IP header that would cause it to address instances across VPC boundaries. They can put anything they want into that 32-bit field. They can strobe across the entire IPv4 address space, and they can't hop across VPC boundaries. A slightly more complex example, same ARP request, but in this case, for whatever reason, our query to the mapping service is corrupt. Rather than querying for the gray VPC, we're querying for the orange VPC. This may be due to a bug in our software, a misconfiguration from one of our operators, or some malicious actor somewhere in the network. The mapping service knows that that server 192.168.0.4 isn't hosting any guests in the VPC named Orange. So we're going to deny that mapping, and we're going to notify an operator. And so even if this mapping request comes out, it's going to be denied. If, for some reason, the misconfiguration, the flaw in the system is greater, and we somehow have a valid mapping for that destination, we can perform the double wrapping, we can send the packet across the physical network, and on receipt, we're going to perform a validation check. And unlike the previous flow, this destination is going to ask, hey, Orange 10.0.0.4, is that there on 192.168.0.4? The mapping service is going to say no. We're going to drop this packet. We're not going to deliver it to the instance. And again, we're going to notify an operator, and we're going to get a human involved. And so in order for packets to flow, all of the parties involved in the flow have to agree on the configuration of the network. The source, the destination, and the mapping service all have to be in agreement.
Can you talk about how you authenticate the mapping service to the layer 3?
That's complicated, and I don't go into how the mapping service authenticates. This talk has to fit in an hour, and so back to the physical network. Layer 3 forwarding. This is how it's been done for years in data centers around the world. I'm assuming /24 net masks, and I've elided a whole bunch of steps because watching people ARP for their peers is boring. So 10.0.0.2 wants to talk to 10.0.1.3 now. We're going across subnet boundaries. We're going to talk through a router. So we're going to ARP. And in this case, we're not ARPing for our eventual destination. We're ARPing for our gateway. And the exact same ARP dance happens, floods, the router responds, and we now learn the MAC address of 10.0.0.1. So now when we send the packet, the layer 2 and layer 3 sources line up, but the layer 2 destination is the router, and the layer 3 destination is our eventual end host, because Ethernet switches forward packets based solely on their MAC addresses. They don't look past that. So the layer 2 switch knows how to forward to the router. Now the router takes this packet, it swaps out the MAC addresses. So the packet that hits the right Ethernet switch has a layer 2 source of the router's interface in that subnet, as a layer 2 destination of the end host. And so now we can deliver this packet on to the end host. So again, how do we do this in VPC? The exact same ARP request that we would have done in the physical network. We query the mapping service, and in this case, the mapping service responds, and it tells us, here's a MAC address for you. You can go format an ARP response to your guest, but this host isn't actually hosted anywhere. This isn't a guest, it's a gateway. So we note that, we cache that mapping, and we send the ARP response back to the guest. So now, the guest formats their packet. It's exactly the same packet they would have sent in the physical network. We do a secondary lookup. We take that guest's packet, we put it aside in a queue, and we send a query to the mapping service, not for the layer 2 destination, but for the layer 3 destination. We do a secondary lookup at the mapping service. The mapping service gives us a mapping. Happens the standard response includes a MAC address, which isn't meaningful in this context. But we also have the physical destination. So now we take that guest packet off of the queue, perform exactly the same double wrapping, and send it directly across the physical network to the destination host. The exact same reverse mapping happens. The destination knows that this is a packet from off subnet, so it performs all of the MAC swapping necessary and delivers the packet on to the destination guest. So as far as these two guests are concerned, they're connected in different subnets across a layer 3 router. But the forwarding path for layer 3 is identical to the forwarding path for layer 2. The traditional way for performing layer 3 forwarding is you drag your packets up to some layer 3 device, the layer 3 device performs layer 3 functionality, and then you send the packets on to the end destination. We don't do that. The robustness of layer 3 flows is exactly identical to the robustness of layer 2 flows. Even though these two guests are on different subnets, as long as the source server and the destination server are both online and can talk to each other and can talk to the mapping service, they can exchange packets across the router. The VPC router is not a single point of failure, and it has an interesting property. The more you plug into it, the faster it gets. It is a router of infinite capacity because it doesn't have a central point of implementation. So this meets our goal. We've now described how layer 2 and layer 3 flows work in a way that is completely decoupled from the physical topology underneath the virtual topology. So now customers are free to lay out their networks however they see fit, using whatever addressing scheme they have, and our compute team is free to place those instances however is optimal to them, and the network doesn't place any additional constraints on it. I'm not claiming that this system is without scaling limits, but we've treated our entire capacity pool as a single pool. I haven't fragmented capacity in separate silos. Those silos aren't actually horizontal scaling. When you've got an array of web servers, each of the web servers is fungible. A request can come into any of the web servers and they can all answer. When I have a customer launching an instance, I have to launch them in the silo that has their router. So it's not actually horizontal scaling. And so by treating all of the capacity as a single pool, I've managed to drive my utilization to exactly the same levels that I had in EC2. So I was asked earlier about caching. I said something really scary here. When the customer sends a packet that's across a layer 3 boundary, we queue it. Queuing packets is scary because you now have a bounded resource. You've got some queue based in memory that is driven by customer behavior that's outside of our control. So one, we're going to have latency jitter. Packets that need to be queued are going to have higher latency across the network than packets that don't need to be queued. And two, I've got this queue, and I'm going into debt. I have to make sure that the guest can't send packets into the queue faster than I can resolve them at the mapping service and get them out of the queue. And because the guest is talking to the queue local to the box and the mapping service is an off-box call, that's a dangerous place to be. And so what we actually do is we run a little mapping service replica on each of our physical servers, and they're constantly polling the central mapping service. The end behavior of the system is exactly as I've described. The mapping service organizes virtual network information into topics. And it knows where every single resource in the network is placed. And so if a physical server attempts to subscribe to a topic, for example, if 192.168.0.4 attempts to subscribe to the blue topic or to the orange topic, we know that's an error, and we fire exactly the same alarm we would have fired in the inline query case. So we still have all of the same alarming in place, but in practice, we have 100% cache hit ratio. The physical server has all of the mappings that it needs for all of its packet translations for all of its peers at all times. And so we don't have to rely on timeouts or TTLs or anything like that. These caches are actively managed, and the mapping service is constantly pushing down network updates. And so we can very rapidly and consistently push out configuration changes to the entire network with our administrative tools. So because of this implementation, because I'm not allocating a slice of a virtual router to a customer, we don't charge for VPCs. You can create a VPC, you can leave it sitting there with no instances running, it costs you nothing. You can leave it sitting there with instances running, it costs you nothing. We don't charge for subnets. Rather than having 4,096 or however many it is that my switches support, and having to say this is a constrained resource and I want people to be able to use them, but I want to minimize how many of them they have to use. Because of the way we've implemented subnets, you can have as many of them as you can cram into the CIDR block of your VPC. And because of the way the virtual network is implemented, because we haven't made our packet flows any more expensive, the cost for instances and the cost for traffic within the VPC is exactly the same as the cost for EC2 Classic. This has an unfortunate side effect. We have a tradition of dropping prices in AWS. And unfortunately, I don't think we'll ever drop price on VPC. This is a slide I stole from Laura Gritt's talk that I mentioned earlier. November 10th, 2010 is the day we turned off the last physical web server in North American retail. So if you've browsed Amazon.com since November 10th, 2010, The page you saw was rendered by an instance running in a VPC. We follow the industry. We track the academic papers. There's a ton of interesting research in this space. But this is not a research project for us. This isn't a science project that we're producing very prettily formatted tech documents. This is a robust, mature product. This is going to be the 4th year that we carry the holiday peak for Amazon.com. So this is a major line of business for us. This is something we've been doing for a long time. So far in this talk, the only thing I've talked about is EC2 instances. But the slide that I opened the talk with showed all of our other services. And so over time, we've been adding more services. You have your VPC, you can launch your instances, but now you can launch RDS databases, you can launch Redshift clusters, and they're all connected to your VPC. Werner touched on this in his keynote. And so now you can bring these other services inside of your perimeter. Now your client sitting in your on-prem database can connect directly to your Redshift cluster without having to go out over the internet. Now you have access to internal data sources, and all of your existing BI tools can connect directly. And so we're looking at VPC not as a way of connecting EC2 instances together, but as the future of the network in the cloud. This is the platform on which we're investing all of our innovation. So when we launched VPC, the transition's amazing. We started off with VPN connections. These are standard IPsec tunnels engineered over the internet. We've since added direct connect, so you can hand off to us on fiber or copper at 1 gig or 10 gig speeds, private connections, no exposure to internet availability, much lower latency, much flatter latency profiles. A lot of our more security-sensitive customers have asked for security group egress filtering. In VPC, security groups do egress filtering, so you can configure both inbound and outbound permit rules, and that's only available in VPC. We have network ACLs. Many of our customers have a mental model of networks as instances, machines that have IP addresses that are close to each other do jobs that are similar. And machines that have IP addresses that are far apart do jobs that are different. So this subnet is my web servers, this subnet is my application servers, and I express my filtering rules between those subnets. With network ACLs, if you have a compliance regime that requires you to do that, or if you have internal governance rules, you can do that. We have routing tables. This is really difficult to wrap your head around, but interesting functionality. You can apply more specific routes per subnet, and this gives you the opportunity to use EC2 instances as network appliances. So you can either build up your own using standard tools, or we've got the AWS Marketplace where we have a whole bunch of ISVs that have standard products that you know and love, hopefully, in your existing data centers. And you can pull those out and you can run them as EC2 instances, and you can make EC2 instances part of your network topology. And so we've enabled the ecosystem there. We've unblocked a lot of innovation. And part of that is elastic network interfaces. These are basically Ethernet cards in the cloud. So it has a MAC address, it has an IP address, it has a bunch of configuration associated with it, and you can unplug it from one machine and plug it into another machine and dynamically add more. And so this is how you plumb EC2 instances into your network topology. And another common ask from our customers was multiple IP addresses per interface. So we've also delivered that. And again, that's only available within VPC. And one of the things that Werner touched on in his keynote was our new C3 instance family with enhanced networking. And he breezed past this pretty quickly, but I think it's an awesome, awesome feature. This is hardware virtualized networking. We're doing SR-IOV. We're actually forwarding a virtualized hardware NIC into the DOMIO, into the guest. And so you get wireline rates. We're measuring latency in microseconds, and the packets per second throughput has gone up to some ridiculously large number. And it comes with all of the VPC features. So security groups and network ACLs, all of the things that we just talked about are available with enhanced networking. And again, that's only available within VPC. So as you're designing products, you run into this spectrum where you have things that are simple on one side and things that are complicated on the other. And often, the simple things are limited, and the complicated things are flexible. And there's no value judgment here. I own both an oscilloscope and a micrometer, and I have both of them. I intend to keep both of them. Lugging the oscilloscope around to check a battery is very silly, but trying to troubleshoot a clock circuit with a multimeter is just not going to happen. And so this spectrum exists. It's good. There are good, valuable tools at many points along this spectrum. But EC2 fell more towards the limited and simple end of that spectrum. There weren't a lot of concepts for you to understand in order to take advantage of EC2. We had private IP addresses, we had public IP addresses, maybe you wrapped your head around elastic IP addresses. And that was quick and easy to get started. You made one API call, you called run instances, and you were off and running. But there wasn't a lot there. There wasn't a framework for us to hang more advanced functionality. And then we launched VPC. VPC has this very rich networking topology, has all of these interesting features. You can have instances that don't even have public IP addresses. You've got network ACLs. But there's a tremendous amount more that you have to do. You have to think about CIDR blocks. You have to pick a network range. You have to lay out subnets. So you get a lot more value. You have to invest a lot more. And so one of the things that we launched earlier this year is what we're calling default VPC. The best description of this is a blog post by Jeff Barr in March of this year. So you show up as a new customer at 3 o'clock in the morning, type in your information, and you call run instances. This is the EC2 Getting Started Guide as it's existed for years. It's code compatible with all of the stuff that our customers have been writing for EC2. And you can go ahead and you can launch and terminate instances to your heart's content. And then at any time, you can look behind the curtain, and it turns out that there's always been a VPC behind your instances. And so then you can take advantage of it. You can tell us about your home data center, bring up a VPN connection, take advantage of all of the advanced functionality of VPC, but you don't have to deal with it up front. So back to the spectrum, we have a single converged product that allows customers to pick where they land on the spectrum. And they can move where they are on the spectrum at any time. You can get started quickly with EC2. You launch an instance. You go through the Getting Started Guide. You don't have to master all of those concepts. And then at any time, you can just choose to turn on more and more bits and pieces and take advantage of the complexity of VPC. I had initially titled this Other VPC Sessions, or Other Interesting Sessions, but PowerPoint kept making the text smaller and smaller. So it's just Interesting VPC Sessions. I think a couple of these have already happened, but we're planning on posting them to YouTube so you can catch them again later. And thank you very much.